So today's a big day for our vertex operator algebra playlist, and we're going to look at our first juicy example. But before we do that, I want to recall a definition and look at some things that we've done previously. So a vector superspace, V, which is the direct sum of V0 and V1, is a vertex algebra if we may endow it with infinitely many products. In other words, if we take A and B in V, and n in the integers, then there is a notion of an nth product between a and b, which we denote by a sub n b. So we just put the subscript on the a to think of it as the nth product. Sometimes instead of thinking of this as a product, we think of this as endowing a with infinitely many linear maps, but that gets back to kind of the algebraic notion of looking at a product as a linear map associated with the guy on the left, but that's kind of neither here nor there. Okay, and then also we've got this thing called a vertex operator associated with a. So we call it YAZ, or sometimes just A of Z, and it's going to be the sum over all integers, A sub n Z to the minus n minus 1. So this A sub n means that when you attack a vector B from the left, you have like A sub n B. So that gives you this like formal power series in terms from the vector space. And then we've got these rules that this must follow. So first of all, there exists a vacuum element, which is in V0. In other words, it's an even element, such that if you take this vacuum element and do the nth multiplication between it and A, you will get A only when n is equal to -1, and you'll get 0 any other time. So in other words, this is the identity map for n equals -1, and it's 0 everywhere else. Then next we have something called the creation property, which says that a sub -1 on the vacuum equals a, so that is the multiplication that creates a. And then a sub n on the vacuum is equal to 0 if n is bigger than or equal to 0. So that gets you kind of below some sort of minimum energy or something. And then next we have that if A is in VI and B is in VJ, then A sub n times B is in VI plus J mod 2. So in other words, if they're both in V0, then this product and any of these products for any integer n is going to be in V sub 0. So if you start off with two even elements, you take any of their products, you get an even element. If you start with one even and one odd element, regardless of which one's which, you will get an odd element. And furthermore, if you start with two odd elements, in other words, A is in V1 and B is in V1, then A sub nB is in V1 plus 1 mod 2, but that's V0. So the product of two odd elements is an even element. Okay, and then next we've got this rule which is called the lower truncation axiom, or sometimes called the locality axiom. And that says that for all A and B in the vector space V, there exists a natural number n such that A sub nB is equal to 0 for all n bigger than or equal to n. And then that is equivalent to this following statement about vertex operators. And we can prove this equivalence later once we have a handle on this internal structure a bit more. So we've got z minus w to the n, so that's an expanded binomial, times the commutator azbw equals 0. And then finally, we've got this special linear map called the translation operator. We're going to call it T. It goes from V to V. And it satisfies the following rule. Y of TAZ is equal to the formal partial derivative with respect to Z of YAZ, or A of Z if we want to write it like that. So in other words, if we know the vertex operator for a vector A, then we know the vertex operator for a translated copy of that vector A. In other words, T evaluated at A. Okay, so let's look at what we've done previously. So previously we talked about what were the correct types of vector spaces to think about when we're thinking about modeling vertex algebras. And really the best and simplest vector spaces to get your head wrapped around in order to understand this field would be polynomial rings with infinitely many variables and generalizations of that idea. So maybe we've got a true polynomial ring and infinitely many variables that everything commutes. So we'll look at an example of that later. Or perhaps we've got something that looks like a polynomial ring and infinitely many variables, but it is non-commutative. But we know something about the commutation relations among all of the elements. And then in the last video, we defined something called the normally ordered product. So we first saw that in general, it is impossible to multiply two vertex operators. You will get something that does not formally converge or not algebraically converge. But we could fix that by doing this normally ordered product, or this thing called the Wick product, named after a physicist. And I'm going to denote that by these open circles, AZ, BW. So that's going to be equal to A plus Z, BW plus BWA minus Z. And I should say here that this is really -1 to the parity of A times the parity of B. So that's going to pick up a minus sign if they are both in V1. And then I should say, if everything here commutes, then this is exactly equal to A of Z, B of W. And so that's kind of nice. Okay, so next, we still have to figure out how to work with objects like this. So what if we take the negative third multiplication of A with B, look at that element, and then take, for instance, the negative second multiplication of that with another vector C. But it turns out that we can understand that by understanding the vertex operator defined by A, N, B, Z, where N is just some integer. So if we understand that vertex operator in terms of the original vertex operators, then we can understand this type of product. And that brings us to our first big definition, which is how do we deal with these negative infinite products? So in other words, how do we deal with A sub minus 1b, A sub minus 2b, A sub minus 3b, and so on and so forth? And we can actually define them pretty nicely using this notion of the normally ordered product. So we've got y of A minus n minus 1b z. In other words, the vertex operator of this vector right here is given by 1 over n factorial times the normally ordered product of the nth derivative of A of Z times B of Z. So we're going to look at stuff like this quite a bit in the future, but today we're just going to look at a commutative vertex algebra. So we won't actually need to look at the normally ordered product, we just need to look at the normal product, because the normally ordered product turns into the regular product of these vertex operators if you have something that is commutative. Okay, so let's maybe go ahead and clean this up and then get going with our example. So before we get going with our example, I want to prove a really important but very simple fact that has to do with commutative vertex algebras. And that is, if these two vertex operators, so A of Z and B of W, commute, then A of n B equals 0 and B of n A equals 0 for all n bigger than or equal to 0. In other words, if we have commutativity here, then this truncation condition happens with just n equals 0. So notice I've put an if and only if here, but this if and only if is something that maybe needs to be proved once we get a handle on all of these infinitely many products. So if we have a truly completely commutative vertex algebra, then we only need to deal with these negative products, but we have a handle on those negative products from the previous board. And so, like I said before, this is an if and only if statement. We're going to focus just on the first direction in this video. Okay, so let's maybe go ahead and do it. So we're going to suppose that these two vertex operators commute. So in other words, AZ with BW commutes. But now I want to expand each of those as series. And so let's notice that that is exactly the same thing as the sum over all integers m and the sum over all integers n. So we've got this doubly infinite double sum, and then am bn of multiplied by z to the minus m minus 1, w to the minus n minus 1. In other words, am bn, where we think of those as like maps associated to the mth product with a and the nth product with b, is equal to 0. And this has got to be true for all m and n in z. But now if those thought of as maps are equal to 0, then that means if we evaluate them at another vector c, we will also get 0. But furthermore, we can expand this out to a sub m b sub n c minus 1 to the parity of a times the parity of b, b sub n, a sub m, c. So we have that is equal to 0. Great. And so notice I haven't used the straight commutator here. I've used something that's sometimes called the super commutator. So if both of these are odd elements, I get an anti-commutator of am and bn. But if one of them is an even element, then I just have the normal commutator there. Okay, great. Now, the next thing that I want to do is set m to be bigger than or equal to 0, anything bigger than or equal to 0, and then we'll set n to be equal to -1 in this equation up here, along with c is equal to the vacuum. So notice that is going to give us am b sub -1 on the vacuum minus -1 to the parity of a, parity of b, b sub -1 a sub m on the vacuum is equal to 0. But we know that all of this is equal to 0 by the creation property of a sub m with the vacuum, this guy up here, and then also by the creation property, we have b sub -1 on 1 is just b. So in other words, we have a sub m on b is equal to 0. And that was true for all m bigger than or equal to 0. And then we can very, very similarly prove this for b sub n on a is equal to 0. So this is an important thing to notice about commutative vertex algebras, is if you have a commutative vertex algebra, then you essentially don't have to worry about any of the non-negative products. Okay, so let's maybe go ahead and clean this up and we'll finally look at an example. So we're finally ready for our first example. So this is a commutative vertex algebra generated by a single element. So I'm going to call it V, and it is also the polynomial ring in infinitely many variables, x sub -1, x sub -2, x sub -3, and so on and so forth. So like I said, this is the vertex algebra generated by x, which we're thinking about x as being x sub -1 on the vacuum, but the vacuum in this case is just the number 1 in the complex numbers. Great, so we've taken care of what the vacuum is. Now maybe we need to take care of what the translation operator is. So next, let's define t going from v to v in the following way. So we're going to let t evaluated at x sub -m1. So that's an element in v. So that's going to be equal to -m minus 1 x sub -m minus 1 on 1. So for example, if we take t on x, we'll get x sub -2, 1. If we take t on x sub -3, we'll get 3 x sub -4, 1. Great. So obviously, since 1 is just a complex number here, we don't really need to write it, but we'll write it just so that it looks like a more typical vertex algebra. Okay, great. So now that we've got a handle on t when it attacks linear terms from our vertex algebra, let's talk about how to define the vertex operator. So here we're going to define y of xz. So this is going to be the sum over all integers of x sub n, z to the minus n minus 1. But by the lemma that we proved on the previous board, we know that we only have to deal with the negative products. So we can expand this out. This is going to be x sub minus 1. So that is the z to the 0 coefficient, plus x sub minus 2z plus x sub minus 3z squared, and so on and so forth. So that's how we'll define that. And then next, inductively, we can define the following. So we'll define y of x sub minus m minus 1z to be equal to something that's like the nth derivative of this, but it's not exactly the nth derivative of this. So it's going to be 1 over m factorial, and then the nth derivative with respect to our formal variable z of yxz. So in other words, it's the nth derivative of this guy right here. So in general, so as a quick example, we have y of x sub minus 2 on 1, or the vacuum of z, is going to be equal to, well, notice m is equal to 1 in that case. So we have 1 over 1 factorial, and then the first derivative with respect to z of yxz. But now that's going to be this guy right here. So it's going to be the derivative of x sub minus 1 plus x sub minus 2z plus x sub minus 3z squared plus dot, dot, dot. So in other words, this vertex operator is going to be given by x sub minus 2 plus 2x sub minus 3z plus 3x sub minus 4z squared, and so on and so forth, just by taking those derivatives. Okay, great. So now let's maybe clean this up, and then we'll look at what does a vertex operator of an arbitrary term look like, and maybe how do we take the translation operator of something that's a little more general. Okay, so we've seen the general structure of this vertex algebra when we're looking at linear terms. What I mean by a linear term is something that's like a coefficient times x to the minus m. But what if we've got something that's a little bit more general? And this is spurred by the fact that by linear algebra, we have a basis for this v, and maybe we won't talk about the basis, but v is clearly spanned by the following set. So this is spanned by monomials that are of the form x sub minus m1 minus 1 all the way up to x sub minus mk minus 1 on the number 1, or the vacuum. Or you can just think about it as this monomial with k terms there, where these mi's are all bigger than or equal to 0, which keeps our subscripts negative just kind of as needed. So since we're spanned by monomials like that, we need to talk about what does the vertex operator of a monomial like that look like, and what does the translation operator of a monomial like that look like. And we'll see that those are one and the same question. So we'd like to look for a vertex operator for an arbitrary monomial like that. If we can get a handle on what that vertex operator looks like, we're in good shape. So, but if we recall from the definition that we had on the first board, involving negative products and the normally ordered product, we know that the vertex operator of x sub minus m1 minus 1, x sub minus m2 minus 1, all the way up to x sub minus mk minus 1, z, is going to be equal to the following. So we've got 1 over m1 factorial multiplied all the way up to 1 over mk factorial. And then the partial derivative of z, the m first partial derivative of z of yxz multiplied all the way up to the partial derivative of z, the mkth partial derivative of z, of yxz. And so that's just inductively constructed by the definition that we had on the first board involving just two of these multiplied together. Okay, great. So notice that this is going to allow us to find the translation operator of a more general vector. So let's maybe look at an example of that. So we want to find the translation operator of x sub minus 2x, for example. So let's notice that that is going to be the coefficient of z to the 0 in the vertex operator of the translation operator of x minus 2 xz. Great, kind of from this definition over here. Then the next thing that we can do is bring this translation operator out of the vertex operator and take a derivative. So that's going to tell us this is the coefficient of z to the 0. In other words, the constant term of the partial with respect to z of yx minus 2xz. Great. But the next thing that we can do is split this up using our formula up here. So this is going to be the coefficient of z to the 0 power, in other words, the constant term of the partial with respect to z of the partial with respect to z of yxz multiplied to yxz. Great. So where this yx minus 2xz turned into this product right here by our definition of the general vertex operator up here. Great. So now let's go ahead and take the partial derivative of this thing using the product rule. So notice that's going to give us the coefficient of z to the 0 of, now we have the second partial with respect to z of yxz times yxz, and then plus the partial with respect to z of yxz squared. Again, using the product rule there. Okay, so let's maybe lift this up to here, and then we'll finish this example off. Okay, so we've brought this up. So our goal is to find the coefficient of z to the 0, in other words, the constant term in this object. So we've got the second derivative with respect to z of yxz, that vertex operator, times yxz, plus the first derivative with respect to z of yxz squared. Now I'm going to use the fact that we only have positive powers, I should say non-negative powers of z in all of these expansions. We don't have any negative powers of z, and that's because we're in a commutative vertex algebra. Okay, so let's expand this a little bit and see what we get. So we're going to have the coefficient of z to the 0, in other words, the constant term, then the second partial with respect to z of yxz. So that's going to be, like I said, the second partial with respect to z of x sub minus 1 plus x sub minus 2 z plus x sub minus 3 z squared. And we actually don't need any more terms for this calculation. And then that's going to be multiplied by yxz, so that's x sub minus 1 plus some more terms. We're not going to need any more for that part of the calculation either. And then we need to add this to the partial with respect to z of x sub minus 1 plus x sub minus 2z, and then that whole thing squared. Great. So next, we have to take the coefficient of z to the 0 from here. So let's do the little calculation right here. So if we take the second partial with respect to z here, we're going to have 2 times x minus 3 plus terms that contain a z. Then, if we take the partial with respect to z here, we're going to have x sub minus 2 plus terms that involve a z. So, extracting a constant term means we need to extract a constant term here and a constant term here, and then a constant term from both parts of this product. And notice we don't have any negative powers of z because we're in a commutative vertex algebra. So from this first bit, we're going to get 2 x minus 3 x minus 1 plus the second bit is going to be x minus 2 times x minus 2. So that would be the translation operator on x minus 2x. Okay, let's maybe clean this up and we'll do some more hands-on examples. So we just did an example applying the translation operator to a quadratic element to give a flavor for how to do that in general, using these axioms over here and the fact that this thing is commutative. So the next thing that I want to do is talk about the component operators of the vectors themselves. So notice that we discussed before that elements of this vector space look like the following monomials or sums of monomials. So we've got like x sub minus 1 squared times x, where x is like x sub minus 1 on 1, or like x sub minus 3, x sub minus 2, 1, or x sub minus 5 squared, x sub minus 3, x. Where again, every time you see an x at the tail end, you can just think of that as like x sub minus 1, 1. So maybe here are a couple of questions. So the first question has an easy answer, but maybe it's not super satisfying. And that is, how would you do something like x sub minus 3? So that is an element in this vector space. And then attack maybe x sub minus 2, x sub minus 1, plus x sub minus 4. So how would you do that multiplication? Well, all you would do is just stick x sub minus 3 on the tail end of this. So in other words, we would write this as equal to x sub minus 3, x sub minus 2, x sub minus 1, plus x sub minus 3, x sub minus 4. But then, using the commutativity, we can rewrite this as x sub minus 4, x sub minus 3. So if we take x and take the negative third operation between x and this is exactly what we get. Okay, good. Now, what about something a little bit more general? What about something like this? So what if we wanted to do x sub minus 3x, and then the negative second multiplication of that with x? Well, we have to go back to our vertex operators. Maybe that's the easiest way to do it. And what I want to notice is that because we're taking the negative second multiplication, that's going to be the coefficient of z to the 1, because 1 is the same thing as negative negative 2 minus 1, of the vertex operator x sub minus 3x z evaluated at x. So this is the kind of thing that we have to construct. But by the stuff that we had on the previous boards, we know how to take that vertex operator. It has to do with some derivatives. So we have the coefficient of z to the 1. And now we're going to rewrite this as 1 over 2, the second partial derivative of yxz times yxz on x. So let's maybe talk our way through that. So we've got a minus 3 here. And by our definition on the first board, we know that that is going to split this thing up into these two parts, where we don't need a normally ordered product because we have a commutative vertex algebra here. Okay, great. Now let's expand this out into terms again. So notice we need the coefficient of z to the 1 of, well, let's maybe bring this half out front here. And then we've got the second derivative with respect to z of x to the minus 1 plus x sub minus 2 z plus x sub minus 3 z squared, and so on and so forth. And then that's going to be multiplied by x sub minus 1 plus x sub minus 2 z plus dot dot dot. And then finally all of that is going to mash onto z. Great. Now what I want to notice is we can take this derivative pretty easily. So taking this derivative, we'll see that these two parts will go to 0 just by the power rule. And from the second derivative of this, we'll have 2x sub minus 3. And then from the second derivative of the next term, which is x sub minus 4z cubed, we'll have 3 times 2 x sub minus 4z plus dot dot dot. Now look at what we need to do. We need to take the product of these two things and then extract the linear term. In other words, the z to the 1 term. So we can achieve a z to the 1 term by this part times this part, or by this guy right here times this guy right here. So either way we do it, we'll get a z to the 1 term. So let's see what we get. So the half is going to kill this 2 and this 2. And by the red underlines, we'll have x sub minus 3, x sub minus 2 on x. And then by the purple underlines, we'll have plus 3, x sub minus 4, x sub minus 1 on x. So you ask, how do we reassociate this product? And we do it, and we get it expanded out into these two terms. Okay, so maybe I'll go ahead and clean up the board, and then I'll give you guys a couple of these to try that are in this same spirit. Okay, so good news. We've finally got an example of a vertex algebra, but they're quite complicated, so it's useful to get your hands dirty. So I want to give you guys a couple of problems to try, but before we do that, I want to introduce the notion of a monomial in standard form. So a monomial in V, where we can think about that as our vertex algebra or our polynomial ring, is in standard form if it looks like this. X sub minus m1 minus 1 multiplied all the way up to x sub minus mk minus 1, where m1 is bigger than or equal to m2, which is bigger than or equal to m3, all the way down to mk, which is bigger than or equal to 0. So notice we don't have to worry about positive products here because, again, we're in a commutative vertex algebra. So here are some examples of monomials in standard form. So x sub minus 5, x sub minus 4, 1. X sub minus 3 squared, x sub minus 2, x. Where again, we can think about that x as x sub minus 1, 1 if you want. And here are some non-examples. So we've got x sub minus 4, x sub minus 7, 1. So those are commuted in the wrong order. So this has a simple fix of just rewriting it as x sub minus 7, x sub minus 4, 1. Because again, we're in a commutative vertex algebra. But then this guy is associated incorrectly. So we've got x sub minus 4, x sub minus 2, sub minus 3, 1. So we've got to do some tricks involving the vertex operator and the stuff that we did on the previous boards in order to expand that. So here are some homeworks for you guys to try to get your hands dirty with these kind of calculations. So let's write the following two things as a combination of monomials in standard form. So the first one is the translation operator applied to x sub minus 4, x sub minus 2, x. So that'll follow like the first example that we did. And the second one is x sub minus 4, x sub minus 3, and then the negative second multiplication of that object onto x sub minus 1 times x sub minus 1. So I think working out each of these will give you guys a feel for how to do calculations in this setting. So we're going to come back in the next video and look at a couple of more examples of commutative and supercommutative vertex algebras. But here's a good place to stop.